A quiet shimmer spreads across the Milky Way when you look at it from far enough away. From above, the galaxy appears almost serene, a vast, spiraling disk of stars arranged like soft brush strokes of light, turning slowly in the darkness. But as the viewpoint drifts closer, the calm surface begins to reveal its turbulence. The spiral arms blur into thick clouds of dust and stellar nurseries. The glow sharpens into millions of individual suns, each with its own history, its own motion, its own quiet struggle against gravity. And then, as the perspective drops toward the centre of this immense whirling disk, the night tightens. The stars crowd closer together. They stop behaving like the orderly constellations familiar from Earth's sky and start to move more like a swarm, fast, tangled, each one tugged by invisible forces far stronger than anything found in the outer galaxy. Light dims as dust thickens, hiding the core behind dark lanes that cut across the sky like cosmic smoke. Somewhere in that darkness lies a paradox, a supermassive black hole that barely shines at all. For a long time, the centre of the Milky Way was simply a shadowed region, mysterious, inaccessible, and strangely quiet. The galaxy around it produced brilliant supernovae, glowing nebulae, and bright clusters, but the core remained muted. Even when radio telescopes first detected a compact, powerful source deep within the constellation Sagittarius, nothing about it suggested the kind of ferocity associated with the engines that light up distant galaxies as quasars. Other galaxies have cores that blaze with radiation, powered by black holes feeding so rapidly that they outshine all their stars combined. Yet ours sits almost dormant, as if it has slowed its breathing to a whisper. A black hole of more than 4 million solar masses should be anything but subtle. Its gravity is intense enough to force stars into orbits tighter and faster than the planets around the Sun. It should, by all conventional expectations, pull in gas from its surroundings, heating it to millions of degrees until the whole region glows with X-rays. But Sagittarius A star, the black hole at the Milky Way centre, seems content to wait. It barely consumes anything. The gas around it swirls chaotically, yet rarely falls inward. The radiation it emits is faint, flickering occasionally, but usually resting just above quietness. This strange calm is part of what makes the galactic centre feel like another world entirely. Earth sits about 26,000 light-years from Sagittarius A star, orbiting the galaxy in a region where stars are spaced relatively far apart. Here, the night sky looks peaceful because gravity is gentle. But near the centre, gravity dominates every moment. Stars there move hundreds of kilometres and hundreds of miles per second. The region is thick with dust, magnetic fields, hot gas and turbulent winds from massive stars, yet all of it is governed by a single object that cannot be seen directly. Sagittarius A star is not the kind of black hole that announces itself with a blazing halo. It does not roar with the energy of matter falling inward. Instead, it behaves more like a gravitational keystone, a point of immense influence that shapes the orbits of everything nearby without emitting much light at all. If the galaxy were a great wheel, Sagittarius A star would be its hub, silent, fixed, and essential. And that silence is deceptive. The black hole is not inactive because it lacks power. It is inactive because the environment around it is surprisingly inefficient at feeding it. The gas in the galactic centre is too hot, too turbulent, too magnetically tangled to fall inward easily. Instead of spiralling smoothly down toward the event horizon, much of it swirls chaotically and escapes. The black hole waits, patient, consuming only a trickle. It shines with less than a millionth of the brightness a typical supermassive black hole of its size could produce. Yet its influence reaches far beyond its dim glow. The motions of nearby stars trace out an invisible curve in space, revealing a gravitational well so steep and so compact that no other known object could explain it. Some of those stars, like the famous S2, swing around the black hole in orbits that would tear apart any normal cluster. Their motion is the signature of a gravitational anchor, an object with the mass of millions of suns compressed into a space smaller than the orbit of Mercury. From Earth, we cannot see Sagittarius A star directly with our eyes. Dust absorbs the visible light from the galactic center, blocking it as effectively as a thick smokescreen. But radio waves, infrared light, and X-rays slip through the haze, and through them we learn that the darkness is not empty. It contains a quiet titan, shaping the galaxy in silence. The paradox becomes clearer the closer we look. The most massive, the most influential object in the Milky Way is nearly invisible. It does not shine, it does not blaze, it does not tear its surroundings apart in an obvious way. Instead, it governs through gravity alone, a force that cannot be seen but can be felt across tens of thousands of light years. The sun orbits it. Every star, every cloud of gas, every drifting planet follows a path determined, in part, by this quiet hunger at the centre. For billions of years, the Milky Way has turned around this single point of darkness. It has been a stable anchor in a galaxy full of motion, a presence that affects everything without calling attention to itself. And as we drift inward in imagination, moving past the crowded stars and the twisting clouds of gas, the idea settles in. This quietness is not emptiness. It is restraint. Before we go deeper, if you enjoy exploring the quiet wonders of the cosmos like this, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow, and it keeps these journeys alive. In a universe filled with violent collisions, blazing quasars, and brilliant explosions, Sagittarius A star stands apart. It is a reminder that not all power announces itself. Some of it waits in darkness, shaping everything around it through silence. Long before astronomers understood what lay in the centre of the Milky Way, they knew something unusual had to be there. The night sky offered hints that the galaxy was not simply a scattered distribution of stars, but a vast organised system with a core. Even in ancient times, the densest region of the Milky Way, arching through Sagittarius, stood out as a brighter, more crowded patch of sky. But its true nature remained beyond reach until the early 20th century, when a few scientists began to suspect that the galaxy's heart might be far stranger and heavier than anyone imagined. In the 1910s and 1920s, the American astronomer Harlow Shapley was among the first to map the Milky Way on a grand scale. Using globular clusters, those ancient spherical swarms of hundreds of thousands of stars, he traced their positions across the sky and realized that they formed a pattern. The clusters weren't distributed randomly. They formed a lopsided halo with a clear centre offset from the sun. That centre, Shapley concluded, must mark the true heart of the galaxy, and it did not lie anywhere near Earth's location. Instead, it was thousands of light years away in the direction of Sagittarius, hidden behind thick interstellar dust. This was a revolutionary idea. Up until then, many had assumed the sun was near the centre of the Milky Way, a comforting but anthropocentric notion. Shapley showed that we lived far from the middle, about 30,000 light years by his early estimates. He also suggested that the region around the galactic centre must contain extraordinary mass, enough to bind the entire disk of stars into a coherent system. But in Shapley's time, the tools to see through the dust simply didn't exist. The centre remained invisible in optical light, an opaque mystery even as its gravitational influence became undeniable. Jan Oort, the Dutch astronomer whose name still echoes throughout galactic dynamics, added another layer of insight in the 1930s. By studying the motions of stars near the Sun, he deduced that the Milky Way rotates as a disk, and that the centre must contain an immense concentration of mass. Like Shapley, he pointed to Sagittarius as the location of this gravitational focus. But the true nature of the central object, or objects, remained speculative. Oort imagined a dense cluster of stars or gas, but nothing like the modern concept of a supermassive black hole. The term itself didn't exist yet. Walter Baade, working at Mount Wilson Observatory in the 1940s, used wartime blackout conditions in Los Angeles to achieve unprecedented visibility at optical wavelengths. He mapped populations of stars in the galactic bulge, finding older, redder stars packed tightly in the central region. Baade's observations refined distances and helped create a modern picture of the Milky Way's layout, but even he could not see the core itself. It remained shrouded in interstellar dust, a puzzle waiting for a new kind of astronomy to unlock it. That breakthrough came not from an optical telescope, but from a radio antenna built by an engineer who wasn't even searching for cosmic mysteries. In the early 1930s, Carl Jansky, a young physicist working for Bell Telephone Laboratories, was tasked with investigating sources of static that interfered with transatlantic radio communication. The assignment was purely practical: find the origin of the annoying hiss that disrupted long-distance calls. Jansky constructed a massive rotating antenna mounted on old Ford Model T wheels, allowing him to sweep the entire sky. What he discovered was astonishing. Among the thunderstorms and local interference was a faint, steady hiss that returned every 23 hours and 56 minutes, matching the sidereal day, not the solar one. This meant the signal came from beyond Earth. By plotting the strength of the signal, Jansky traced its peak to the constellation Sagittarius. He didn't yet know the significance of that region, but astronomers quickly recognized that Jansky had detected radio waves from the direction of the galactic center. It was the first time the Milky Way had been heard rather than seen. Yet the discovery was ahead of its time. Radio astronomy was still in its infancy, and for years after Jansky's 1932 detection, the field developed slowly. It wasn't until after World War II that radio astronomy blossomed. New antennas and interferometers allowed astronomers to map the sky in radio wavelengths, revealing structures hidden behind dust. In the 1950s and 1960s, work by Jack Piddington, Ronald Bracewell, and others revealed a bright, complex region of radio emission near the galactic center. They divided it into components based on spectral features and brightness. The central region became known as Sagittarius A. The name Sagittarius A star came later. In 1974, astronomers Bruce Ballack and Robert Brown used the newly upgraded Green Bank interferometer to observe the galactic center at high resolution. They noticed a compact, extremely bright radio source at the exact center of Sagittarius A, far more concentrated than the surrounding emission. To distinguish it as a special, point-like object, Brown appended an asterisk. In radio astronomy, the asterisk often designates an excited state of atoms. Here, it was a playful nod to something exceptional, something distinct from the broader Sagittarius A complex. Sagittarius A star was tiny, so small that even with the best instruments of the time, it appeared almost point-like. Yet it was powerful enough to suggest extreme density. Something compact was sitting at the center of the galaxy, emitting steady radio waves. But what kind of object could produce such a signal? By the 1970s, the idea of black holes had matured. Once speculative solutions to Einstein's equations, they were now considered plausible astrophysical objects. Quasars and active galactic nuclei had been discovered in the 1960s, suggesting that supermassive black holes powered the cores of distant galaxies. If other galaxies could host such giants, why not the Milky Way? Still, there was a problem. Our galactic center did not behave like a quasar. It lacked the brilliant jets and luminous accretion disks that made other supermassive black holes shine across billions of light years. Sagittarius A star was quiet. Too quiet. It did not fit neatly into the growing picture of violent, hungry galactic nuclei. The Milky Way seemed strangely quiescent. Hints of something massive lurking in the dark came from measurements of gas dynamics near the core. Astronomers observed ionized gas orbiting at astonishing speeds, far faster than gravity from normal stars could explain. By the late 1970s and early 1980s, both infrared observations and radio measurements indicated that a tightly packed region of enormous mass sat within a space no larger than our solar system. The evidence pointed toward an invisible compact object, but the precise nature of that object remained unsettled. Critics wondered whether a dense cluster of neutron stars or exotic objects might mimic the gravitational signature of a black hole. The puzzle grew sharper as technology improved. Infrared telescopes began to penetrate the dust clouds obscuring the galactic center. Detectors became more sensitive, allowing astronomers to track the motions of individual stars near Sagittarius A star. Early observations showed rapid shifts in position, stars moving at hundreds of kilometers and hundreds of miles per second. The speeds were extraordinary, far beyond anything seen in the solar neighborhood. Each measurement tightened the noose around the possible explanations. By the late 1980s, it was increasingly difficult to deny that something immense and compact ruled the center of the Milky Way. Its mass was enormous. Its size was minuscule. It was dark, invisible, yet gravitationally dominant. The simplest explanation, a supermassive black hole, grew stronger with each passing year, even if direct proof was still out of reach. The history of discovering Sagittarius A star is not just a story of telescopes and measurements, it is a story of shifting expectations. For decades, astronomers believed the galactic center must be crowded and active. Then, when radio signals revealed something strange, they struggled to connect the faint hiss with a central engine of such immense power. The idea that the heart of the Milky Way could harbour a supermassive black hole that barely shines seemed contradictory. But as evidence accumulated, the contradiction itself became the clue. A quiet, compact, gravitationally overwhelming object was precisely what theory predicted a supermassive black hole might look like when deprived of fuel. Long before we imaged it, long before stars like S2 traced perfect arcs around it, Sagittarius A star had been whispering its presence through radio waves. Jansky heard it as static. Shapley mapped its gravitational realm without ever seeing it. Bard saw the stars of its environment sharpen in the Californian wartime darkness, and Oort inferred its mass quietly, mathematically, long before anyone imagined a black hole could lie beneath the Sagittarius sky. It was a mystery revealed piece by piece, first by gravity, then by radio waves, then by infrared light. A mystery that grew sharper, not louder, as scientists approached the truth. Only later would we learn just how compact, how dark, and how quietly powerful the object at the center truly was. In the late 20th century, the mystery at the heart of the Milky Way narrowed to a small patch of sky no wider than a pinpoint. It was there, in the deepest layers of interstellar dust, that astronomers suspected something massive and unseen was hiding. But suspicion alone was not enough. To prove that Sagittarius A star was a supermassive black hole, they needed stars, real stars, moving around the object with the unmistakable signature of an immense gravitational pull. The problem was that no ordinary telescope could see them. Between Earth and the galactic center lies a staggering wall of dust. Over tens of thousands of light-years, microscopic grains of carbon and silicates scatter and absorb visible light so completely that the region becomes opaque. For generations, astronomers were effectively blind to the motions of stars near Sagittarius A star. They could study gas flows by radio or X-ray emission, but they couldn't track the silent ballet of individual stars whose orbits could reveal the mass hidden in the dark. Infrared astronomy changed everything. Unlike visible light, infrared radiation passes through dust far more easily. It does not scatter as severely. By shifting to longer wavelengths, especially around 2 microns, astronomers could peer through the murk and glimpse stars that had never been seen before. The earliest infrared images of the galactic center in the 1970s and 1980s revealed a dense cluster of stars moving at extraordinary speeds. But the images were still blurry, smeared by both Earth's atmosphere and the limitations of early detectors. The stars appeared as flickering, unstable points. Tracking their motion precisely was impossible. Then, in the 1990s, 2 separate teams set out to solve the problem with unprecedented ambition. On one side of the world, Andrea Ghez and her group at UCLA began using the Keck telescopes on Mauna Kea in Hawaii, giant 10-meter mirrors capable of gathering enormous amounts of infrared light. On the other side, Reinhard Genzel and the Max Planck Institute team used the European Southern Observatories facilities at La Silla, and later the Very Large Telescope, VLT, in Chile. Both teams faced the same obstacle: Earth's atmosphere. The constant turbulence in the air blurs astronomical images, making stars near the galactic center appear as shifting blobs rather than stable points. To overcome this, they turned to adaptive optics. Adaptive optics works like a high-speed corrective lens. Every few thousandths of a second, a computer measures how the atmosphere is distorting incoming starlight. It then flexes a deformable mirror, sometimes hundreds of times per second, to counteract that distortion. The result is remarkable. A star that would ordinarily look smeared becomes pinpoint sharp. Features that had been invisible suddenly appear as crisp structures. With adaptive optics operating on the Keck and VLT telescopes, the fog lifted. The galactic center emerged in stunning clarity. Stars that had once blended together now separated cleanly, dozens of them packed into a region barely a fraction of a light year across. These stars, known as S-stars, were unlike any others in the galaxy. They were young, shockingly young for such a chaotic environment, and moving at breakneck speeds, hundreds to thousands of kilometers per second, hundreds to thousands of miles per second. Their motions hinted at an invisible mass pulling them inward. Among them was S2. S2 became the Rosetta Stone of galactic center dynamics. It is a bright, massive B-type star with an orbital period of about 16 years. In the mid-1990s, both the Keck and VLT teams began following its motion night after night, year after year. Each new measurement revealed a star tracing out a graceful but dramatic ellipse around an unseen point. As S2 approached its closest point to Sagittarius A star, it accelerated to nearly 8,000 kilometers per second, around 5,000 miles per second. No other known object could force a star into such a tight, fast orbit unless it contained millions of solar masses compressed into an incredibly small region. Other stars followed. S38, with a roughly 19-year period, traced a similar ellipse. S55, also known as S0102 in the Keck dataset, was even more valuable, as it had one of the shortest known orbits, around 12 years. The faster the orbit, the more precisely astronomers could constrain the mass at the centre. These stars acted like interstellar test particles, governed purely by gravity. Their orbits allowed astronomers to apply Kepler's laws, Newton's gravitational equations, and later Einstein's general relativity to determine what lay at the focus. The results were astonishingly consistent. All the orbits pointed to the same compact, invisible object. All required a mass of about 4 million suns confined within a region no larger than the orbit of Mercury. This was far too dense to be a cluster of stellar remnants. A cluster of neutron stars or black holes would evaporate over time, scattering under its own gravitational interactions. Worse, it would collapse inward due to its own gravitational instability. Only a single supermassive black hole could remain stable under such conditions. The evidence grew stronger every year. In 2002, S2 reached its closest approach, just 120 astronomical units from Sagittarius A star, and the Keck and VLT teams captured it in exquisite detail. Its orbit matched exactly what general relativity predicted for a star near a massive black hole. The gravitational redshift, the stretching of its light due to the intense gravitational field, was measurable. Light left the star slightly weakened, losing energy as it climbed out of the deep gravitational well. This matched Einstein's equations with stunning precision. By 2018, when S2 completed another close pass, the measurements became even more refined. Now, astronomers could detect not only gravitational redshift, but also orbital precession, a subtle shifting of the orbit caused by space-time curvature. Just as Mercury's orbit precesses around the Sun due to relativistic effects, S2's orbit precessed around Sagittarius A star. The effects were tiny but undeniable. They were the fingerprints of a supermassive black hole. One by one, alternative explanations collapsed. A dense cluster of exotic objects would not only be unstable, but would also scatter stars through gravitational interactions in ways not observed. A ball of dark matter would not provide the tight, point-like gravitational focus revealed by the orbital data. A hypothetical exotic star made of degenerate matter would exceed known limits of stability. Every scenario except a black hole became increasingly implausible. The Keck and VLT adaptive optics programs became two of the most important long-term observational campaigns in astrophysics. Over nearly 3 decades, researchers compiled precise positions, velocities, and spectra of dozens of S-stars, building an unparalleled record of motion in the deepest gravitational well of the Milky Way. The work demanded technological innovation, stable funding, and extraordinary patience. Tracking a star for a full 16-year orbit means committing a significant fraction of a scientific career to one dataset. In 2020, the Nobel Prize in Physics recognized the monumental achievements of these efforts. Reinhard Genzel and Andrea Ghez shared half of the prize for the discovery of a supermassive compact object at the center of our galaxy. The award honored not only the individuals, but the decades-long development of infrared astronomy, adaptive optics, and high-resolution imaging that made the discovery possible. The Nobel citation summarized what the stars themselves had revealed. The motions of dozens of objects confirmed that only a supermassive black hole could account for the gravitational pull at the galactic center. Sagittarius, a star, was no longer a theoretical candidate, but a measured, quantified reality. A 4 million solar mass black hole shaping the heart of the Milky Way. What made the discovery so compelling was not just the precision of the measurements, but the elegance of the physics behind them. Orbital mechanics, when applied to stars near such an intense gravitational well, becomes a kind of cosmic handwriting. Each orbit traces out information about the mass, distance, and compactness of the central object. A star like S2 writes its story in curved lines across the sky, and those lines reveal a truth no photograph could capture alone. The stars near Sagittarius A do not move slowly and gracefully like planets in the solar system. They race, their orbits are steep, their accelerations enormous. Yet their motion is predictable, a testament to the power of gravity and the mathematical harmony of general relativity. If one plots their positions over time, they form looping ellipses around a point where no star shines. That empty point carries the weight of millions of suns. It is a dance performed in darkness, illuminated only by infrared light. A dance made visible by humanity's insistence on seeing what lies beyond the dust. And in that dance, astronomers found the most direct evidence possible that a supermassive black hole anchors the Milky Way. By the time the Nobel Prize was awarded, the conclusion had become unavoidable. The galactic center is not held together by a cluster of stellar remnants or an exotic mass distribution. It is shaped by a single object, silent, compact, and overwhelmingly massive. Every star nearby arcs and accelerates under its influence. Every orbit is a tribute to the gravitational well carved into space-time by Sagittarius A star. And so, the mystery that began with Shapley's mapping of globular clusters, that whispered through Jansky's radio hiss, that sharpened through decades of infrared work, finally revealed its answer in the motions of a few stars barely visible through a forest of dust. The centre of the Milky Way contains a supermassive black hole, and we know this not because we see the black hole itself, but because the stars around it dance in patterns that only such an object could command. No matter how precise the measurements of S-stars became, the true essence of the object they orbited remained hidden behind one of nature's most absolute boundaries, the event horizon. To describe Sagittarius, a star in physical terms is to enter a realm where ordinary intuition collapses, replaced by equations that reshape space and time themselves. And yet, even without seeing the black hole directly, the properties of its structure can be inferred with remarkable clarity. The most fundamental characteristic of Sagittarius A star is its mass, roughly 4 million times that of the Sun. Mass is the defining signature of a black hole, the quantity that curves space-time and sets the scale for everything else. It determines the gravitational pull, the size of the event horizon, the intensity of tidal forces, and even how quickly matter must orbit to remain stable. A mass of 4 million suns is enormous, yet for a supermassive black hole, it is actually modest. Many active galactic nuclei harbour black holes 100 times larger or more. From this mass, astronomers can calculate the Schwarzschild radius, the distance from the centre at which the escape velocity equals the speed of light. For Sagittarius A star, the Schwarzschild radius is about 12 million kilometres, roughly 7.4 million miles. That is the size of the event horizon for a non-spinning black hole of this mass. The event horizon itself is not a physical surface, but a point of no return, where the geometry of space-time becomes so steep that even light cannot escape. Anything crossing that boundary disappears from the universe in a way no other object can match. Though the Schwarzschild radius provides a useful measure, real black holes rarely remain perfectly still. They rotate. Sagittarius A star is almost certainly spinning, though its exact spin rate remains uncertain. A rotating black hole is described by the Kerr solution of general relativity, which twists space-time into a spiraling funnel. Rotation drags space around with it, a phenomenon called frame dragging, making the geometry more complex than a simple sphere. Instead of a single event horizon, spinning black holes have an outer horizon and an inner horizon, separated by a region of intense gravitational shear. If Sagittarius A star spins rapidly, the event horizon shrinks slightly in some directions, and space-time becomes more distorted. The innermost stable circular orbit for matter changes too. For a non-spinning black hole, that orbit lies at 3 times the Schwarzschild radius. For a rapidly spinning one, it can shrink to nearly 1 radius in the direction of the spin. This affects the motion of gas and the potential brightness of the accretion disk. Yet for all these extraordinary properties, massive curvature of space-time, event horizon tens of millions of kilometers across, frame dragging that twists space itself, Sagittarius, a star, remains faint, almost inexplicably faint. Black holes themselves do not shine, but the matter falling into them normally does. In many galaxies, gas accretes onto the central black hole in vast swirling disks, heating to millions of degrees as it spirals inward. These disks emit enormous amounts of light, from X-rays to ultraviolet to optical wavelengths. In the most extreme cases, the infall of matter becomes so efficient that it lights up the galaxy as a quasar, outshining billions of stars. So why does our own central black hole remain almost invisible? The answer lies in the physics of accretion under conditions where the gas supply is extremely inefficient. The region surrounding Sagittarius, a star, is filled with hot, tenuous plasma blown off by massive stars in the central cluster. Winds from Wolf-Rayet stars and supergiants create a chaotic environment of turbulent streams, shock fronts, and magnetized clouds. But most of this material never reaches the event horizon. Instead, It forms a radiatively inefficient accretion flow, an unusual state in which most of the energy released by falling matter does not radiate away as light, but is carried off by the gas itself. In a typical accretion disk, gas cools efficiently, losing energy as radiation and spiraling inward as it sheds angular momentum. But near Sagittarius A star, the gas is so hot and sparse that collisions between particles are rare. Without collisions, the gas cannot cool effectively. It becomes trapped in a hot, turbulent state where particles orbit chaotically, often losing so little energy that they are flung outward rather than falling inward. The result is that only a tiny fraction of the available material actually crosses the event horizon. This is why Sagittarius A star emits only about 1/1000th of the luminosity that would be expected from a quasar of similar mass. It is practically starving. The little light it does emit comes from interactions in the inner accretion flow, synchrotron radiation from electrons spiraling along magnetic field lines, Bremsstrahlung from high-energy collisions, and occasional magnetic reconnection events that produce short-lived flares. These flares, observed by telescopes like Chandra and XMM Newton, provide brief flashes of activity, but are the exception rather than the rule. Adding to the faintness is the structure of space-time around the black hole itself. In the steep gravitational well, photons emitted near the event horizon lose energy as they climb out. This gravitational redshift weakens their intensity. At the same time, light emitted close to the black hole can be bent inward, swallowed, or redirected, further dimming the apparent brightness. The shape of Sagittarius A star's space-time funnel also influences how matter moves. If the black hole is spinning, magnetic fields can become twisted, building up tension that eventually snaps, releasing energy in bursts. These bursts may account for some of the infrared and X-ray flares observed, but even then, the total energy output remains tiny compared to other galactic nuclei. Another factor is the angular momentum of infalling gas. Sagittarius A star sits in a turbulent environment where streams of gas from different directions collide and interfere. Unlike quasars, which often have large, coherent disks feeding their black holes, the Milky Way's center receives chaotic, irregular flows. Sometimes, gas approaches with angular momentum so high that it never falls inward at all. Other times, streams cancel each other, briefly allowing more efficient accretion. But overall, the net inflow is small. Even if Sagittarius A star were fed more consistently, it might not react in the way a quasar does. Supermassive black holes exhibit a wide range of accretion states. At extremely low feeding rates, like those near our galactic center, the physics shifts dramatically. Radiatively inefficient accretion flows become common. Outflows and winds carry away much of the energy. The black hole essentially chokes, unable to build a bright disk. In such a regime, most of the gravitational energy released by falling gas is converted not into radiation, but into kinetic energy and heat within the accretion flow itself. Some models suggest that much of the matter entering the region near the event horizon is actually ejected before crossing it, driven outward by pressure gradients and magnetic forces. This unusual accretion state gives Sagittarius A star a personality quite different from that of quasars. It is quiet, not because it lacks power, but because it rarely has the opportunity to express that power through light. If one could look at the black hole from a few astronomical units away, which no physical observer could survive, the scene would be dim compared to active galactic nuclei. The inner region would glow faintly in millimeter and infrared wavelengths. The accretion disk, if it even forms coherently, would appear turbulent, puffy, and irregular. Particles would zip around at relativistic speeds, but the gas would be too thin to radiate efficiently. From Earth, this faintness poses a challenge. Even with enormous telescopes, the emission from Sagittarius A star is difficult to image. Interstellar scattering blurs millimeter waves, smearing the signal. Variability on timescales of minutes complicates long integration times. And because the black hole is so small compared to its distance from Earth, the apparent size of the event horizon is tiny, equivalent to seeing a tennis ball on the moon. Yet this faintness is also what makes Sagittarius A* scientifically valuable. Most supermassive black holes studied in detail are active, luminous, and energetic. But Sagittarius A* gives astronomers a rare glimpse into the low-luminosity regime, a phase that may represent the majority of a black hole's lifetime. Galaxies likely spend far more time in quiet states than in quasar phases. The Milky Way's centre, therefore, may reflect a common, understated chapter in black hole evolution. Understanding this regime requires combining observations across the electromagnetic spectrum. Radio telescopes capture the faint millimeter glow. Infrared observatories detect the flickering emission from hot electrons. X-ray telescopes catch the rare, high-energy flares. Together, they form a picture of a black hole not roaring but simmering, its accretion flow delicate, unstable, and full of subtle interactions. Even the Event Horizon Telescope, which imaged Sagittarius A* directly, revealed a soft, blurred ring rather than a sharp, bright crescent like the one seen around M87 star. This is partly because Sagittarius A* is smaller and more variable, but also because its accretion flow is so diffuse that light emerges from a complex shifting tangle of plasma. All of this contributes to the paradox at the heart of our galaxy, a supermassive black hole that barely glows, a gravitational titan that quietly shapes the Milky Way without drawing attention to itself. Its event horizon is vast, its space-time geometry extreme, yet its appearance from Earth is subtle, almost ghost-like. The anatomy of Sagittarius A reveals a structure defined not by light, but by absence, an event horizon tens of millions of kilometers wide, surrounded by a turbulent sea of hot, underfed plasma, a space-time funnel that curves inward with ferocious strength, but expresses that strength with minimal radiation, a gravitational well that anchors the galaxy even as it remains nearly invisible. The quietness is not emptiness. It is simply the natural outcome of a black hole living in a low-luminosity state, starved of steady fuel, surrounded by chaotic flows that rarely allow it to feed. And in that quietness lies one of the purest expressions of gravity in the universe. A supermassive black hole revealing itself not through brightness, but through its geometry, its influence, and the stars that orbit it in the dark. From a distance, Sagittarius A* looks like a contradiction. A 4 million solar mass object should radiate with extraordinary intensity if fed even a moderate flow of gas. Standard accretion models predict that a black hole this size, supplied with the amount of material available in the central parsec of the Milky Way, ought to shine 1 million times brighter than it does. Instead, it barely glows at all. Its luminosity is so low, roughly 1 billionth of the Eddington limit, that early astrophysicists genuinely wondered whether they had miscalculated the mass. But the mass is correct. What's unusual is the behavior of the material around it. Sagittarius A* is surrounded by hot plasma, stellar winds, and magnetic turbulence that make the environment look busy and chaotic, yet almost none of it falls inward. The black hole's neighbourhood resembles a storm with no rainfall, plenty of clouds, plenty of motion, but somehow gravity never receives its expected offering. Ordinarily, accretion disks form when gas loses energy and spirals inward, shedding angular momentum in the process. In bright, active galactic nuclei, this inward cascade becomes extremely efficient. Gas compresses and heats, collisions intensify, and radiation carries away energy so quickly that the disk cools and continues to collapse. It's a runaway cycle. Cooling encourages infall. Infall releases more gravitational energy, and the released energy makes the system shine. Sagittarius A* breaks this cycle. The plasma near the galactic center is extraordinarily hot, often exceeding tens of millions of degrees. At these temperatures, protons and electrons move so rapidly that they rarely collide. Without frequent collisions, the plasma cannot radiate efficiently. This leads to what astronomers call a radiatively inefficient accretion flow, or RIAF. In ARIAF, most of the gravitational energy that would normally be emitted as light is absorbed by the gas itself, raising its temperature rather than letting it cool and fall inward. The result is counterintuitive. The hotter the gas becomes, the less likely it is to accrete. Instead of spiraling inward, the gas puffs up, becoming a thick, turbulent structure rather than a thin disk. Much of the material gains enough energy to escape entirely, being driven outward by pressure gradients and magnetic forces. The inflow becomes a kind of cosmic conveyor belt that rarely delivers anything to the horizon. Another obstacle is angular momentum. Falling into a black hole isn't just a matter of being pulled inward. It requires losing the sideways motion that keeps gas in orbit. In Sagittarius A star, the gas streams come from dozens of massive stars in the central region, each blowing off winds in different directions. Rather than forming one coherent rotation, these streams collide, shear, and tangle. They often cancel each other's motion, but not in a clean way. The turbulence they generate sometimes prevents any large, stable disk from forming. Without such a disk, angular momentum cannot be transferred efficiently, and accretion slows to a crawl. Magnetic fields complicate the picture even further. The galactic center is full of magnetized filaments and twisted loops of plasma. As the gas swirls, magnetic tension can act like a spring, storing energy until it snaps in sudden reconnection events. These events produce infrared and X-ray flares, brief moments when Sagittarius A star seems to wake up. But these bursts do not feed the black hole significantly. They release energy from the plasma itself, not from material crossing the event horizon. What little gas does reach the inner region must contend with increasingly steep gravitational gradients. Near the innermost stable orbit, where matter begins its final spiral, the gas becomes optically thin and wildly turbulent. Electrons emit synchrotron radiation as they twist along magnetic field lines, but even this emission is faint compared to what quasars produce. Most of the electron's energy is simply swallowed. Most of the ion's energy is carried outward by winds. The black hole receives only a trickle of matter despite being surrounded by an environment that appears at first glance ripe for feeding. To understand just how underfed Sagittarius A star is, it helps to compare it to M87 star, the supermassive black hole in the centre of the galaxy Messier 87. M87 star is roughly 1,500 times more massive than Sagittarius A star, yet it consumes matter far more efficiently. Its accretion disk is large, coherent, and capable of sustaining powerful jet activity. The Event Horizon Telescope images of M87 show a bright crescent, light from a disk that is radiating strongly as matter falls inward. Sagittarius A star, by contrast, appeared as a softer, blurrier ring in the 2022 EHT image. Its emission is not dominated by a large, stable disk, but by a turbulent, hot, dilute flow. While M87 channels magnetic energy into twin relativistic jets that blast material outward at near-light speed, Sagittarius A launches no such jets. If a jet exists, it is either extremely weak or extremely small. The energy budget simply isn't there. Active galactic nuclei, those brilliant cores visible across the observable universe, show just how far Sagittarius A star is from its high-luminosity cousins. In quasars, accretion rates approach the Eddington limit, generating radiation so intense that the surrounding galaxy can be shaped by it. Winds blow out star-forming gas. Jets pierce the intergalactic medium. The whole structure of the galaxy responds to the fury of the central engine. Sagittarius A star is the opposite, a dormant or weakly active nucleus whose influence comes not from radiation but from gravity alone. It has no significant feedback on the Milky Way today. Its energy output is dwarfed by ordinary stars. supernovae, and even the collective winds of massive stars in the galactic center. And yet, this quietness offers a rare scientific gift. Most supermassive black holes in the observable universe are too far away to study in detail. The nearest active nuclei are still thousands or millions of light years from Earth, and their accretion disks blur together from our perspective. Sagittarius A star is the only supermassive black hole close enough for us to observe individual flares, small-scale plasma structures, and dynamical changes on timescales of minutes. Its faintness allows us to see physics that would be drowned out by brightness in more active systems. We are witnessing accretion at its most subtle. In a sense, Sagittarius A star allows astronomers to study a black hole in its resting state. This may be the default condition for most supermassive black holes in the universe. Galaxies likely pass through quasar phases only briefly, hundreds of millions of years at most. The rest of the time, they live quietly, with their central black holes feeding weakly and sporadically. The Milky Way, therefore, is not unusual. It is simply between meals. The strange calm in our galactic center is not the absence of physics, but a different expression of it. Hot plasma swirling without cooling, magnetic turbulence trapping energy, angular momentum refusing to surrender. The black hole waits patiently. If a major gas cloud or disrupted star ever delivers fresh material into its vicinity, Sagittarius A star could brighten dramatically. It has done so in the past. It will do so again. For now, though, it rests in a state of near starvation, quiet, faint, and profoundly informative. It is a reminder that the universe does not always reveal its power through brightness. Sometimes its deepest mysteries are tucked inside the silence. The closer one moves toward the galactic center, the more the Milky Way stops behaving like an ordinary stellar neighborhood and begins to feel like an entirely different kind of environment. Dense, hot, turbulent, and shaped by forces far more chaotic than anything found near the sun. In this region, stars crowd together with astonishing density, sometimes separated by distances comparable to the size of the solar system, rather than the vast parsecs typical of our local neighborhood. The airless space between them is filled with powerful stellar winds, magnetic filaments, and clouds of gas heated to millions of degrees. If the sun lived in this environment, Earth's sky would never grow dark. This place, the inner few light years around Sagittarius A star, is an astrophysical laboratory unlike any other, a cosmic furnace where the boundaries between order and chaos blur. At the heart of this neighborhood lies a cluster of young, massive stars. Many of them are Wolf-Rayet stars, some of the most extreme objects in the universe. Wolf-Rayet stars shed enormous quantities of mass every year, blowing off their outer layers in furious stellar winds that travel at thousands of kilometers and thousands of miles per second. These winds collide with one another, forming shock fronts that heat the gas to X-ray emitting temperatures. The central parsec of the Milky Way is suffused with this violent, churning atmosphere. It is remarkable that these young stars exist here at all. Conditions near the galactic center are hostile to star formation. Gravitational tides from the black hole stretch molecular clouds, and the turbulence in the gas prevents it from condensing easily. Yet somehow, millions of years ago, a massive cloud collapsed near Sagittarius A star, creating a burst of star formation that produced a population of hot, luminous stars. Many of them orbit in a coherent disk-like structure, while others move in more scattered paths, each one contributing its own fierce wind to the surrounding maelstrom. The combined effect of all these winds is a constantly shifting system of high-pressure, magnetized plasma that sometimes falls toward the black hole, sometimes flows outward, and sometimes forms arcs and filaments bent by the gravity of nearby stars. The region's temperature and density conditions fluctuate wildly, shaping the accretion environment that keeps Sagittarius A star unusually faint. Farther out, stretching tens of light years from the center, lies the circumnuclear disk, a massive, rotating ring of hot molecular gas. This disk is not like the delicate protoplanetary disks that form planets around young stars. Instead, it is a rugged, clumpy, and highly dynamic structure, dominated by shocks and turbulence. Its mass is enormous, equivalent to hundreds of thousands of suns, yet it remains only loosely bound, with gas clouds continually colliding and fragmenting. The circumnuclear disk acts like a reservoir of potential fuel, but very little of it actually reaches the black hole. The gas within the disk orbits too far out, too fast, and too chaotically to fall inward easily. Instead, streamers of gas occasionally peel off and move toward the inner region. These streamers, long thin structures shaped by magnetic fields and gravitational forces, wind among the stellar clusters like cosmic rivers. Some may eventually feed Sagittarius A star, though most dissolve or scatter before reaching the inner accretion zone. Signs of the region's turbulent history echo through the environment. Observations with Chandra and XMM Newton have revealed patches of diffuse X-ray emission that appear to come from old supernova remnants. One such remnant, about a light year from the black hole, is thought to have exploded within the last few thousand years, a recent event by astronomical standards. The shock waves from this explosion still ripple through the surrounding gas. Infrared images show bow shocks, arc-like structures that form where the winds of fast-moving stars collide with the ambient medium. These bow shocks trace out the motion of stars as they plough through dense regions of gas, compressing material into curved, glowing outlines. Some stars generate colossal bow shocks that stretch for hundreds of astronomical units, sculpted by the combined effects of radiation pressure, stellar wind, and the gravitational influence of Sagittarius A star. This environment is not only shaped by stars and gas, it also contains a set of enigmatic objects that have puzzled astronomers for more than a decade, the G objects. The first of these, G1, was identified in 2004, but it was G2, discovered in 2012, that captured the world's attention. G2 appeared as a small, dusty cloud moving on a highly eccentric orbit that would bring it perilously close to the black hole. Many astronomers predicted that it would be torn apart during its close passage in 2014, potentially triggering a bright flare as the material fell into Sagittarius, a star. Telescopes around the world prepared for a rare feeding event. But nothing dramatic happened. G2 passed its closest point, stretched slightly, and continued on its orbit with surprising resilience. Instead of being shredded like a delicate gas cloud, it behaved as if it contained something more substantial, perhaps a star hidden within the dust. This unexpected durability forced astronomers to rethink the nature of G objects. Further observations revealed several more: G3, G4, G5, and G6, each with orbits that took them deep into the gravitational well of Sagittarius A star. Like G2, these objects were dusty, infrared bright, and unusually compact. Some showed signs of tidal stretching near pericenter, but none were destroyed. One intriguing hypothesis is that G objects are stellar remnants of recent mergers. The galactic center's extreme densities make stellar collisions far more likely than in ordinary space. When two stars merge, they can produce a swollen, dust-enshrouded object that gradually contracts over decades or centuries. During this contraction phase, the object appears red, dusty, and extended, much like the G objects. Another theory suggests that they may be binary stars that spiraled inward under gravitational torques, merged due to the tidal influence of the black hole, and now exist as newly formed hot cores wrapped in leftover material. In this view, the G objects might represent a population of rejuvenated stars, stellar phoenixes rising from the ashes of two predecessors. Regardless of their origin, their survival near the black hole provides a fascinating clue about the dynamics of the region. Their dusty shrouds interact with the harsh environment, Their orbits trace out gravitational pathways influenced by both the black hole and the surrounding cluster. They serve as probes of the physics governing the inner light year. The entire neighbourhood is a study in contrasts. Young stars surrounded by old remnants, hot plasma flowing among cold molecular clouds, ordered stellar disks embedded in turbulent gas, quiet black hole accretion zones adjacent to ferocious stellar winds. It is a region caught between creation and destruction, where stars are born under unlikely conditions and gas clouds are sculpted by forces that should tear them apart. What becomes clear, the deeper we peer into this extraordinary environment, is that Sagittarius A star does not exist in isolation. It is embedded within a dynamic ecosystem, a cosmic metropolis teeming with stellar giants, shredded clouds, shock fronts, and mysterious objects. The black hole's faintness is not a sign of simplicity, but the outcome of an enormously complex interplay of forces that constantly shape, feed, and starve it. Everything near the galactic centre moves quickly, collapses quickly, evolves quickly, and yet, amid this perpetual turbulence, a strange balance persists. The black hole waits at the centre of a neighbourhood that never rests, influencing its surroundings not through bursts of power, but through steady, relentless gravity. It is a place where even silence has structure, and where every object, from Wolf-Rayet stars to dusty G objects, tells a part of the story of how galaxies grow, burn, and shift over time. For most of its time, Sagittarius A star emits only a faint whisper of radiation, barely enough to stand out against the glowing background of the galactic centre, but every so often the quiet breaks. A sudden flare erupts, brightening the black hole's surroundings by factors of tens or even hundreds. These flares appear in the near-infrared and X-ray bands, lasting anywhere from a few minutes to a couple of hours. They rise sharply, fade slowly, and vanish without warning, leaving astronomers to wonder what briefly disturbed the stillness around the event horizon. The space telescopes that keep watch, Chandra in X-rays, XMM Newton with its sensitive detectors, and the Keck Observatory in infrared, have recorded hundreds of such events. Each flare is a tiny spark against the vast canvas of the black hole's environment. Yet they are among the clearest windows into what happens in the innermost regions of a low-luminosity accretion flow. When Sagittarius A star brightens, even for a moment, we glimpse physics that is otherwise drowned in silence. The first X-ray flares were detected in the early 2000s by Chandra. The observatory's exceptional angular resolution allowed scientists to isolate emission from a region only a few light minutes across, essentially the immediate environment of the event horizon. When the first flare erupted, it stunned researchers. Over a period of less than an hour, the black hole brightened by roughly 100 times its normal X-ray output. The flare climbed rapidly, plateaued briefly, then decayed in a smooth curve. Nothing like this had been observed from Sagittarius A star before. Infrared telescopes soon detected their own version of these flares. The Keck telescopes and the VLT using adaptive optics observed short-lived brightenings in the near-infrared that often coincided with X-ray events. The two emissions were clearly related, but infrared flares occurred more frequently, suggesting that they represented a more common, lower-energy version of the rarer X-ray bursts. The timing, brightness, and spectral properties of these flares pointed to a shared origin. Sudden acceleration of electrons to relativistic speeds, energies so high that the electrons spiral around magnetic field lines and emit synchrotron radiation. In X-rays, the emission can arise from inverse Compton scattering, where infrared photons get boosted to much higher energies by colliding with fast-moving electrons. But what triggers these sudden energy injections? One compelling explanation is magnetic reconnection, the same physical process that powers solar flares. In the turbulent flow of hot plasma around Sagittarius A star, magnetic field lines are twisted, tangled, and stretched by differential motion. When the tension becomes too high, the magnetic field snaps into a lower energy configuration, releasing energy explosively into the surrounding gas. Electrons caught in this event are launched to relativistic speeds, creating a rapid burst of radiation. These reconnection events likely occur very close to the black hole, within a few Schwarzschild radii, where magnetic pressures and gravitational shear are at their strongest. The short duration of the flares suggests that the emitting region must be compact, on the scale of light minutes or less, consistent with the inner accretion zone. One of the most intriguing developments in recent years is the idea that some flares are produced by hotspots, localized clumps of plasma orbiting extremely close to the event horizon. As these hotspots swirl around Sagittarius A star, they move at a significant fraction of the speed of light. Their motion produces periodic modulation in the infrared brightness, a subtle flicker that reflects both their orbit and the extreme curvature of space-time near the black hole. In 2018, coordinated observations with the VLT's gravity instrument achieved something unprecedented. They tracked the motion of bright infrared flares and found that the emission moved in a circular path at a radius of about 6 to 10 times the Schwarzschild radius. That location corresponds closely to the innermost stable circular orbit, ISCO, predicted by general relativity for a black hole of Sagittarius A star's mass. If the hotspot interpretation is correct, these flares are not just brief brightenings, they are markers tracing space-time itself. The timing and frequency of the observed motion align with orbital periods of tens of minutes, exactly as predicted for material orbiting near the ISCO of a 4 million solar mass black hole. Even more impressively, the observed polarization of the infrared light suggests that the emission originates from electrons spiraling along ordered magnetic fields, just what one would expect from synchrotron radiation in a magnetically dominated plasma. Chandra and XMM Newton add a complementary perspective. While infrared observations locate the orbiting hotspots, X-ray flares provide clues about how energetic the electrons become. The shape of the X-ray spectrum indicates that the electrons responsible must reach energies of tens of gigaelectronvolts, a level difficult to achieve without strong magnetic reconnection. When both infrared and X-ray flares occur simultaneously, it suggests a linked process. Reconnection pumps energy into the electrons, creating infrared synchrotron light, and the same electrons boost some of those photons into the X-ray range via inverse Compton scattering. Keck observations help fill in the gaps between these events by monitoring the black hole over long periods. Their dense datasets provide the statistics needed to understand flare frequency, intensity, and evolution. The combined picture from all these instruments reveals a dynamic, flickering environment where the plasma is constantly shifting. Magnetic fields are constantly reconfiguring, and electrons are constantly being accelerated to extreme energies. Another insight comes from how quickly the flares rise and decay. The sharp onset suggests a sudden release of magnetic energy, while the smooth decline reflects cooling and expansion of the emitting region. The timescales, minutes to hours, match the orbital periods expected near the ISCO, strengthening the case that these flares originate from the very cusp of the black hole's gravitational well. Even the shape of the flare light curves contains information. Some flares exhibit quasi-periodic oscillations, where brightness waxes and wanes with a regular pattern. These oscillations may represent the beaming and lensing of light from a hot spot as it orbits, with relativistic Doppler boosting brightening the emission when the spot moves toward us. Gravitational lensing can magnify the emission when the spot moves behind the black hole, adding spikes of brightness in ways that only curved space-time can produce. For Sagittarius A star, flares are the rare moments when the invisible becomes visible. Most of the time, the black hole's accretion flow is too diffuse, too inefficient, and too faint to reveal its inner workings. But when reconnection tears a magnetic loop apart, or when a hot spot forms in the swirling plasma, or when electrons are pushed to near-light speed, the region lights up just enough to let astronomers watch nature's most extreme processes unfold. These brief bursts, minutes of brightness in millennia of silence, tell us that even a starving black hole has a heartbeat. They show how magnetic fields shape the flow of matter, how particles accelerate near the edge of the event horizon, and how general relativity sculpts the paths of light. In the flares, the quiet giant reveals its hidden pulse. Long before the first image of a black hole appeared on screens around the world, the idea of photographing such an object seemed almost contradictory. A black hole's defining feature is its ability to trap light. Its event horizon is, by nature, a boundary from which no information escapes. And yet, for decades, theorists predicted that the silhouette of a black hole, the shadow carved into surrounding radiation, should be visible if one could observe the region immediately around it with exquisite precision. This was the foundation on which the Event Horizon Telescope, or EHT, was built. The notion that the most extreme object in the Milky Way could cast a visible imprint on the glowing plasma orbiting near its edge. The ambition was extraordinary. It required forming a telescope almost the size of Earth itself. No single observatory, no matter how large, could provide the resolution needed. A telescope capable of imaging Sagittarius A directly would need to distinguish features on scales of tens of micro-arc seconds, equivalent to reading the surface pattern on a coin placed on the moon. Only interferometry, linking widely separated dishes into a single virtual instrument, could achieve such precision. The EHT accomplishes this by coordinating radio observatories around the globe: Hawaii, Chile, Mexico, Spain, France, Greenland, Antarctica, and others, turning Earth into a network of synchronized receivers. By observing the same object at the same wavelength, each pair of telescopes forms a baseline, a slice of information about the incoming signal's spatial structure. The longer the baseline, the finer the resolution. When data from all baselines are combined using techniques of very long baseline interferometry, or VLBI, the result behaves like data from a telescope whose diameter is effectively equal to the maximum distance between the participating sites. This method was revolutionary not in concept. VLBI has existed for decades, but in scale, precision, and purpose. At millimeter wavelengths, where scattering is reduced and black hole emission peaks, the technique becomes extraordinarily challenging. Telescopes must be synchronized using atomic clocks accurate to a few billionths of a second. Weather must be dry and stable across multiple continents simultaneously. Receivers must operate at extreme sensitivity, and the resulting data, petabytes of it, must later be combined with algorithms powerful enough to reconstruct an image from incomplete information. Even the logistics were daunting. Because the data volume is too large to transmit electronically, observatories physically ship hard drives to a central processing center. In some cases, such as the South Pole Telescope, the drives can be transported only when polar weather permits, meaning months of delay. Every step must be perfect. A mismatch in timing, noise in a detector, or a patch of cloud in one location can degrade the entire dataset. Against this backdrop of difficulty, imaging Sagittarius A became one of the most ambitious astronomical projects ever attempted. The EHT had already proven the concept with M87, the supermassive black hole in the galaxy Messier 87. The resulting 2019 image, a bright ring surrounding a dark central shadow, was hailed as a scientific milestone. But even as the world celebrated, HE scientists knew that M87 was, in some ways, the easier target. Sagittarius A presented challenges that went far beyond the already formidable ones faced with M87. The first and most fundamental difference was size in angular terms. M87 star is about 1,500 times more massive than Sagittarius A star, which means its event horizon is proportionally larger. Even though M87 star is much farther away, 53 million light-years compared to our black hole's 26,000, the two end up subtending roughly similar sizes on the sky. But M87 star's larger physical size also means its accretion flow evolves more slowly. A hotspot orbiting near the innermost stable circular orbit of M87 star takes days to complete a revolution. For Sagittarius A star, the same orbit takes mere minutes. This was a profound complication. The EHT observes by collecting data over many hours and synthesizing them into a single image. For M87 star, the slow evolution of the accretion flow meant that the image remained relatively stable over the course of an observing night. For Sagittarius A star, the environment changed so rapidly that the black hole effectively flashed between different configurations while the data were being collected. It was like trying to photograph a whirlpool that rearranges itself every few moments while using a camera that requires a long exposure. The second problem was variability. Sagittarius A star is fickle. Its brightness flickers, flares erupt unpredictably, and turbulence reshapes the flow continually. The EHT had to reconstruct an image from a source that refused to hold still, a task that required sophisticated modelling to separate intrinsic variability from observational noise. The third challenge was interstellar scattering. Between Earth and the galactic centre lies a dense screen of turbulent plasma that scatters radio waves, blurring the image. This effect is similar to the shimmering of stars seen through Earth's atmosphere, but much stronger. At millimetre wavelengths, scattering still distorts the emission enough that the EHT image must be carefully corrected. The scattering screen acts like a frosted pane of glass. It doesn't obscure the source completely, but it smears fine details. Finally, Sagittarius A star is faint compared to M87 star. Low luminosity means less signal to work with, which makes the reconstructions more sensitive to noise. Yet, despite all this, the EHT went ahead with a series of observing runs in 2017 and 2018, pointing the global array at the galactic centre. The data collected during these campaigns were among the most complex interferometric datasets ever produced. They contained not only information about the structure of light near the event horizon, but also the signature of time variability, scattering distortions, and calibration issues unique to observing such a volatile source. To reconstruct an image from this tangled web required a new level of algorithmic sophistication. Multiple independent imaging pipelines were developed to compare results and test robustness. Some pipelines focused on reconstructing static images by averaging over variability. Others attempted to model the time evolution of the emission, effectively producing a set of images that tracked the changing brightness patterns around the black hole. These approaches had to agree, or at least converge on consistent features, before any result could be declared reliable. One of the key insights was that although Sagittarius A star changes on short timescales, certain properties remain stable on average. The presence of a ring-like structure, about 50 microarc seconds in diameter, appeared consistently across reconstructions. This ring corresponds to the photon orbit, the region where light can circle the black hole multiple times before escaping. Its diameter is determined primarily by the mass of the black hole and the geometry of space-time around it. In simulations, this ring appears even when the accretion flow is wildly turbulent. Another stable feature was the central shadow, the dark region inside the ring where the event horizon blocks outgoing light. The existence of such a shadow had been predicted since the 1970s, and its detection in the M87 star image boosted confidence that Sagittarius A star would show a similar structure. The 2022 image of Sagittarius A star confirmed these expectations, though blurrier than the M87 star image, owing to both intrinsic variability and scattering. The result clearly showed a glowing ring with a darker interior. The ring's brightness was asymmetric, with one side slightly brighter than the other. This asymmetry likely reflects relativistic beaming. Emission from plasma moving toward us appears brightened by Doppler effects, while emission from plasma moving away is dimmed. Unlike the M87 image, which featured a well-defined crescent, the Sagittarius A image was more diffuse. The variability blurred out the detailed structure, creating an image that resembled many overlapping snapshots of a rapidly moving flow. But the essential features, the size of the ring, the presence of the shadow, the overall morphology, matched theoretical predictions extraordinarily well. From the measured diameter of the ring, the EHT collaboration inferred a mass for Sagittarius A star consistent with that derived from stellar orbits, roughly 4 million suns. This agreement between independent methods, one dynamical, one imaging, provided compelling confirmation that general relativity's description of space-time around a black hole holds true even in this complex environment. The image also offered insights into the orientation of the accretion flow. The brightness pattern suggested that the plasma rotates in a direction compatible with earlier infrared observations and with the inferred spin axis of the black hole. But uncertainties remain. Sagittarius A star's faintness and variability leave room for multiple interpretations, especially concerning the exact spin rate. Some models favour a moderately spinning black hole, others allow for slower or faster rotation. Still, the 2022 image represented a triumph. It was the first direct visual evidence of the supermassive black hole at the centre of our own galaxy, a structure hidden for millennia behind clouds of dust, now revealed through the incredible precision of Earth-sized interferometry. It signalled that even a source as challenging as Sagittarius A star could be imaged with persistence, innovation, and global collaboration. Just as remarkable as the scientific result was the conceptual shift it represented. For the first time in human history, we were looking at the horizon of the gravitational well around which the entire Milky Way rotates. The glowing ring isn't the black hole itself, it is the last light escaping before falling inward. The dark centre isn't empty. It is a portal to a region of space-time cut off from the rest of the universe. The image is a silhouette cast on swirling plasma by an object that cannot be seen directly, yet shapes the galaxy on a vast scale. It is also an evolving image. Future ET observations, combined with new telescopes and higher frequencies that reduce scattering, may reveal sharper details. Polarimetric imaging, already applied to M87 star, will map magnetic fields near the horizon. Time-resolved imaging may eventually show actual motion within the accretion flow, producing movies instead of static frames. These advances will make Sagittarius A star not just an object of fascination, but one of the most precisely studied black holes in the universe. The challenges that once seemed insurmountable, variability, scattering, faintness, turbulence, became opportunities to refine methods and deepen understanding. In the end, photographing the unphotographable required something more than technology. It required patience to match the slow heartbeat of a quiet black hole and agility to capture its sudden moments of brightness. The result is both a scientific achievement and a quiet reflection of the galaxy itself. A blurred ring glowing softly against the darkness, a shadow at the centre, a presence that cannot be seen directly, yet defines the structure around it. An image of a silence that has shaped our cosmic home for billions of years. The quiet we see today at the centre of the Milky Way is not the whole story. Silence, in cosmic terms, is often temporary. Even the calmest supermassive black hole carries with it the memory of eras when it behaved very differently. Long before we had telescopes capable of peering through the galactic dust, Sagittarius A star lived through phases far brighter, more violent, and more influential than anything it shows now. These episodes left scars, faint echoes of energy, etched into the gas clouds and high-energy structures that surround the galactic centre. They are relics of a time when Sagittarius A star did not merely simmer, but roared. One of the clearest pieces of evidence for this ancient activity comes from an unlikely source: giant molecular clouds tens to hundreds of light years from the black hole. These clouds, composed of cold hydrogen and dust, are massive, calm reservoirs of star-forming material, yet embedded in their coldness is a ghostly glow, X-ray reflections of an outburst that occurred centuries or millennia ago. The technique that revealed this is as clever as it is subtle. Modern X-ray telescopes such as Chandra and XMM Newton observed that certain gas clouds near the galactic center exhibit bright iron fluorescence. This emission occurs when hard X-rays strike iron atoms, knocking out electrons and causing the atom to re-emit light at a specific energy signature. But Sagittarius A star today is too faint to produce such illumination. The fact that these clouds glow means that they were struck by a much brighter X-ray source in the recent past, bright enough that the clouds still shine from the echo. These light echoes behave like delayed reflections. When a flare leaves the black hole, it travels outward and eventually hits distant gas clouds. Because the clouds lie at different distances, the reflections reach Earth at different times. This allows astronomers to reconstruct the history of Sagittarius A star's past activity, like listening to the echo of a shout long after the speaker has fallen silent. What these echoes reveal is striking. Sometime in the last few hundred years, Sagittarius A star must have brightened by factors of 1 million or more compared to its current state. The flare may have lasted months or years, bathing the central tens of light years in intense, high-energy radiation. When scientists tracked the changing brightness in different clouds, they found that the illumination patterns move over time, proof that the black hole's outburst swept outward like a slowly expanding sphere of light, reflecting off one cloud after another. Yet these echoes are only the mildest hints of a far more dramatic past. On much larger scales, thousands of light years above and below the galactic plane, two immense structures loom, detectable only in high-energy gamma rays, known as the Fermi bubbles, after the space telescope that first revealed them in 2010. They extend about 25,000 light-years in each direction. Their edges are sharply defined, almost symmetrical, and filled with hot plasma and relativistic particles. They resemble colossal lobes or inflated cavities carved into the galaxy's halo. The energy required to create these bubbles is staggering. Their total content is equivalent to the kinetic energy of millions of supernovae. Nothing in the galaxy except Sagittarius A star is capable of producing an outburst so powerful and so symmetric. The bubbles are relics, fossil structures left behind by an ancient eruption from the galactic center. The question is, what kind of eruption? Two scenarios dominate current thinking. The first is that millions of years ago, Sagittarius A star experienced a quasar-like phase, driven by a sustained period of accretion. A massive gas cloud may have fallen inward, forming a luminous disk and launching twin jets of material into the galactic halo. Those jets, or the accompanying winds, could have inflated the Fermi bubbles, sweeping up gas and energizing particles along the way. The second possibility is more episodic. Instead of a long quasar phase, Sagittarius A star might have undergone a series of bright, short-lived accretion events. A star passing too close could have been torn apart in a tidal disruption event, or a dense cloud could have briefly funneled matter into the black hole. Even a handful of such events over a few million years could inject enough energy to inflate the bubbles gradually. Supporting this idea are signs of more recent, smaller-scale outflows. Observations with the Chandra X-ray Observatory have detected a narrow filament of hot gas emerging from the galactic center, possibly a weak jet. Radio telescopes have found hints of bubble-like structures on scales of a few hundred light-years. These mini-bubbles may represent the fading remnants of more recent episodes of activity, suggesting that Sagittarius A star still produces occasional outbursts, though nothing close to the power that created the towering Fermi structures. Even today, the black hole's surroundings contain the marks of past eruptions. Gas streamers, long, thin filaments, wind through the galactic centre like smoke trails. Some appear disturbed, bent by shock fronts from old explosive events. Others show signs of having been ionized by powerful ultraviolet or X-ray radiation, remnants of periods when Sagittarius A star shone brightly enough to affect the chemistry of the region. The challenge for astrophysicists is to distinguish between the various layers of history imprinted in the environment. Light echoes reveal activity on timescales of centuries. Mini-bubbles and disturbed gas trace events from tens of thousands of years ago. The Fermi bubbles reflect processes spanning millions of years. Together, they form a complex tapestry of past behaviour, evidence that quietness is not the natural, permanent state of a supermassive black hole. To understand this pattern, one must examine the physics of how a galaxy transitions from active to dormant phases. Quasar activity does not simply stop the instant a black hole runs out of fuel. Instead, the accretion disk gradually thins, loses angular momentum, and becomes unstable. Jets sputter, weakening over time. The surrounding gas cools, recombines and falls back inward or disperses. The radiation field collapses as the energy source dims. This settling process leaves behind chaotic structures, shocked gas, evacuated cavities, glowing shells, and sometimes high-altitude gamma-ray lobes like the Fermi bubbles. Over millions of years, these remnants expand, fade, and eventually blend into the galactic background. The bubbles we see today will continue to drift outward until they become indistinguishable from the halo gas. Their symmetry, a rare feature in the messy galactic environment, is a sign that the outburst which created them was powerful, centrally driven, and likely connected directly to Sagittarius A star. Such transitions from violent to quiescent phases are not unique to the Milky Way. Observations of other galaxies show that supermassive black holes often flicker between active and inactive states, much like a campfire flaring when fed and dimming when left alone. The difference is merely a matter of timescale. Human lifetimes are too short to witness these changes directly, but the evidence of past activity remains etched in gas, radiation, and structure. Sagittarius A star appears to have entered a deeply quiescent phase within the last few million years, after an earlier era when it influenced the galaxy far more strongly. The absence of strong jets, the faintness of its emission, and the calmness of its immediate environment all indicate a black hole living on minimal fuel. But the relics of its past outbursts remind us that this silence is temporary. Should another dense gas cloud fall inward, or should a star wander too close, Sagittarius A star could awaken again, brightening the sky with high-energy radiation and reshaping the galactic environment. Understanding these cycles is critical for understanding galaxy evolution. Active black holes can regulate star formation by heating or expelling gas. They can alter the structure of galactic halos, drive turbulence, and enrich the intergalactic medium with heavy elements. Even a single period of strong activity can influence the next generation of stars. The Milky Way is relatively calm today, but its history shows that it has not always been this way, and that it may not remain quiet forever. In this sense, the galactic centre behaves like a living organism with periods of rest and bursts of activity. The silence we observe now is merely one phase in a long and complex story. The echoes in gas clouds, the vast Fermi bubbles, and the subtle signs of faded jets all tell us that Sagittarius A star once blazed far more brightly and may do so again. The past is still visible in the sky if you know where to look. And in those lingering structures, the black hole's ancient voice still whispers across the galaxy. The present-day quiet of Sagittarius, a star, is only a snapshot in time, a single frame in an evolving story. The galactic center is not static. Gas moves, stars migrate, clusters drift inward, and the black hole itself, silent now, will inevitably encounter new material. To understand what lies ahead for the Milky Way's core, astronomers use long-term simulations that project the motions of gas, star clusters, and black holes over hundreds of millions of years. These simulations trace the slow choreography of gravity as it shapes the future. When scientists model the inflow of gas toward Sagittarius A star, they begin with the region tens to hundreds of light years from the center, where the circumnuclear disk rotates like a turbulent, thick ring. This structure is not stable. It fragments, collides, and reshapes itself continually. Portions of it lose angular momentum through interactions with magnetic fields or turbulent eddies. Other parts are stirred by supernova shocks or stellar winds from massive stars. All of these processes feed irregular gas streams toward the inner few light years, where some material evaporates, some is blown outward, and a very small fraction drifts closer to the black hole. The simulations show that gas inflow is intermittent. Instead of a steady stream, the black hole receives waves of material produced by disruptions in the circumnuclear environment. One of the most dramatic triggers is the passage of a giant molecular cloud into the central region. If such a cloud becomes gravitationally unstable or is tidally stretched, it can fragment and funnel gas inward in a cascade. This process could ignite a future flare or even a bright active phase. But these events happen slowly. A cloud must lose immense amounts of angular momentum before it gets anywhere near the black hole. In some simulations, this takes millions of years. The future of the galactic center, therefore, is not defined by smooth evolution, but by punctuated moments of heightened activity, brief feeding events separated by long periods of quiet. Predicting the next major accretion episode involves estimating when enough material will become available to overcome the angular momentum barrier that currently keeps Sagittarius A star starved. Several candidates exist. One possibility is the collision or close encounter of gas streamers within the circumnuclear disk. When streamers intersect at the right angle, they can cancel out some of their angular momentum and fall inward in a sudden rush. Observations already show that some streamers point almost directly toward the black hole, hinting at future infall. Another scenario involves the infall of a stellar windshell from a cluster of massive stars. These winds create vast bubbles of hot plasma that expand and sometimes stall. If a bubble collapses or encounters dense material, it can channel a surprising amount of gas toward the center. Models suggest that a significant wind-driven inflow could produce an accretion event lasting thousands of years, modest compared to quasar phases but far brighter than today's flickering emission. A third, more dramatic scenario is the tidal disruption of a star. If a star wanders too close to Sagittarius A star, the tidal forces can shred it, scattering its debris into a long, stretched stream. Some of this material escapes into space, but much falls inward, lighting the black hole in a brilliant flare visible across the galaxy. There is no indication that such an event is imminent, but statistically, the Milky Way should experience one every 10,000 to 100,000 years. When it happens, Sagittarius A star will brighten by orders of magnitude, its quiet facade temporarily replaced by violent luminosity. Beyond gas inflow, the future of the galactic center is shaped by the slow inward drift of nearby star clusters. In the dense environment surrounding Sagittarius A star, dynamical friction acts like a gravitational brake. Massive objects moving through the stellar background lose energy, transferring momentum to nearby stars and gradually spiraling inward. Several clusters orbit within a few dozen light years of the center, and simulations indicate that some may sink into the inner region within the next few 100 million years. Their arrival could deliver fresh stars and potentially significant amounts of gas to the vicinity of the black hole. As these clusters approach, they stretch and fragment under tidal forces. Some stars are stripped and join the central cluster. Others may be flung outward in gravitational interactions. The cores of these clusters, dense knots containing massive stars and stellar remnants, could eventually reach distances of mere light years from Sagittarius A star. Their presence would reshape the environment, increasing both the density of objects near the black hole and the likelihood of stellar collisions. Even more intriguing is the possibility that some infalling clusters contain intermediate mass black holes, IMBHs. These elusive objects, with masses between a few hundred and a few 100,000 suns, have long been theorized, but are difficult to observe directly. If an IMBH hides at the heart of a migrating cluster, it could eventually spiral toward Sagittarius A star and merge with it. Such a merger would be one of the most powerful gravitational events in the history of the Milky Way. The energy released in gravitational waves would be enormous, detectable across the galaxy, though not by human instruments unless the merger occurred far in the future when space-based detectors like LISA are active. The resulting recoil from the merger could briefly jolt Sagittarius A star, shifting its position slightly before it settles back into equilibrium. Simulations of galactic nuclei show that IMBH mergers may be a key mechanism by which supermassive black holes grow in the early universe. If the Milky Way hosts even a few IMBHs in its inner halo, which remains an open question, then Sagittarius A star may experience such mergers in its future, contributing to its mass and potentially altering its spin. A change in spin, in turn, affects the structure of spacetime near the event horizon, the shape of the photon ring, and the efficiency of future accretion. A more rapidly spinning black hole might produce stronger jets or generate hotter plasma in its inner accretion flow, even if the overall luminosity remains low. The long-term evolution of the galactic center is therefore a tapestry woven from many interacting threads: gas dynamics, stellar drift, mergers, tidal disruptions, and magnetic turbulence. Some threads lead to quiet outcomes, others lead to violent awakenings. One of the most fascinating outcomes arises from simulations that push tens or hundreds of millions of years into the future. In these distant epochs, after repeated cluster-infall events and possible mergers, the inner parsec becomes more massive and chaotic. Stars scatter more frequently, binary systems drift inward and are torn apart. Some simulations even predict an increase in stellar collisions near the center, leading to the formation of unusually massive, luminous stars, brief beacons that burn hot and die young. Over time, the reservoir of gas in the circumnuclear region may also replenish itself through stellar evolution. Red giants shed their outer layers. Supernova explosions enrich the medium with heavier elements. If enough material accumulates, it could fall inward and ignite another active phase. In this sense, the black hole lives in cycles: accumulation, ignition, quiescence, replenishment, and eventual feeding. Even the large-scale structure of the galaxy plays a role. The Milky Way is slowly interacting with the Sagittarius dwarf galaxy, and in a few billion years it will merge with the Andromeda galaxy. These interactions can funnel fresh gas toward the center, reigniting black hole activity. During the merger with Andromeda, Sagittarius A star and Andromeda's central black hole are expected to spiral together and merge, a titanic collision on a cosmic stage. But these far-off events lie well beyond the horizon of human lifetimes. In the nearer term, the future of the galactic center will likely be defined by modest bursts of activity, the occasional flare-up from a gas streamer, the gradual infall of a cluster, or a rare but powerful tidal disruption event. Between these episodes, Sagittarius A star will remain mostly quiet, its gravity dominating the region, its accretion flow whispering rather than shouting, yet the potential for future ignition always remains. The black hole is not dormant, it is simply waiting for the next opportunity. The galactic center is a dynamic ecosystem, changing at a pace measured in millennia rather than days. Each alteration in gas flow, each migration of a cluster, Each star drifting inward contributes to a slow evolution that will culminate in moments of drama. The future of Sagittarius A star is written not by silence or by violence alone, but by the interplay between the two. Its quiet today is part of a long cycle. Its future, whether marked by gentle flickers or blazing outbursts, will continue to shape the heart of the Milky Way for millions of years to come. Even in its quiet state, Sagittarius A star exerts a kind of gravitational authority that extends far beyond the immediate light years around it. A supermassive black hole is not just an object at the centre of a galaxy. It is the point around which the galaxy's very architecture organises itself. For billions of years, the Milky Way has rotated, rebalanced, and evolved with this compact gravitational well anchoring its structure. The stars around it feel its presence directly. The larger galactic disk feels it indirectly. It is a centre, not in the geometric sense, but in the dynamical sense, shaping motion and matter on scales both intimate and immense. The most direct influence appears in the stellar orbits of the central bulge, a region crowded with hundreds of millions of stars. Within the inner few parsecs, Sagittarius A star dominates completely. Here, stellar velocities reach hundreds of kilometers per second, hundreds of miles per second, and the gravitational potential is steep enough that even small perturbations can send stars into new trajectories. As distance increases, the influence shifts but never fully disappears. The bulge itself, the dense, spheroidal concentration of old stars at the centre of the Milky Way, rotates and swells within a gravitational environment set partly by dark matter, partly by the mass distribution of stars, and partly by the black hole. Simulations of the bulge show that its structure is marginally more compact and stable because Sagittarius A star exists. Without a supermassive black hole anchoring the dynamics, the orbits of stars in the bulge would drift outward slightly over cosmic timescales. The central gravitational well helps confine the stellar population, producing the dense heart of the galaxy we observe today. In this sense, Sagittarius A star acts as a stabilizer, an anchor that prevents the bulge from puffing out too much in response to random motions or tidal disturbances. The galactic bar, a long, elongated structure made of old stars that stretches across the inner few thousand light-years, is shaped by similar influences. Bars form through instabilities in rotating disks, and once formed, they drive gas toward the centre of the galaxy. This gas inflow fuels star formation and can, in principle, feed the black hole itself, but the bar's rotation and shape are subtly affected by the deep gravitational well at the very centre. The presence of Sagittarius A sharpens the central potential, helping maintain the bar's coherent motion by suppressing certain types of orbital chaos that would otherwise weaken its structure over time. Even the pattern speed of the bar, how quickly it rotates, depends on the balance of mass between stars, dark matter, and the central black hole. A slightly more massive Sagittarius A star would slow the bar's rotation, a slightly less massive one could destabilize it. These interactions happen over tens of millions of years, far too slowly to observe directly, but simulations consistently show that supermassive black holes help bars persist longer and regulate how gas flows through them. This brings us to one of the most important connections between Sagittarius A star and the evolution of the galaxy, the regulation of star formation near the core. Star formation is a delicate process requiring cold, dense molecular clouds that can collapse under their own gravity. But the galactic center is anything but delicate. The energy density is high. Tidal forces stretch clouds, magnetic fields twist them, radiation fields heat them, stellar winds from massive stars carve them apart, and underlying all of this is the gravitational pull of the black hole, which sets strict requirements on how close a cloud can come before being torn apart. Within the inner few light years, star formation is nearly impossible. Any cloud drifting too close is shredded into streams of gas before it can collapse. This tidal shear creates a dead zone around the black hole, a region where new stars cannot form. Farther out, the story changes. Between about 5 and 30 light-years from the center, dense molecular clumps can survive long enough to collapse into the young massive stars observed today, but their formation is influenced by the dynamics of gas inflow driven by the bar, the circumnuclear disk, and possibly by past outbursts from Sagittarius A star itself. This interplay is not unique to the Milky Way. Observations of other galaxies show a clear pattern. Central black holes help regulate when and where stars form. They do this not through gravity alone, but through feedback, bursts of radiation, jets and winds that heat gas, disperse clouds, or compress them depending on the conditions. Even in quiet states, black holes shape the temperature and pressure of surrounding gas, influencing whether it cools enough to form stars. Sagittarius. A star may be faint today, but evidence of its past activity suggests it once emitted enough energy to alter the star-forming environment dramatically. The Fermi bubbles, light echoes, and shocked gas structures all point to periods when radiation from the black hole heated large volumes of the central region. During such times, gas would have been prevented from cooling, halting star formation temporarily. Once the outburst faded, gas could cool again, leading to renewed star formation, perhaps explaining the young population of massive stars near the center today. This cyclical pattern, heating, expansion, cooling, collapse, is one of the clearest examples of co-evolution between a galaxy and its central black hole. Galaxies do not grow independently of their black holes. Their histories are intertwined. Observations reveal a strong correlation between the mass of a galaxy's central black hole and the velocity dispersion or mass of its bulge. This relationship, known as the M-sigma relation, suggests that galaxies and black holes grow together. When a galaxy accumulates gas and forms stars, its black hole tends to grow as well. When a black hole becomes active, the energy it releases regulates the host galaxy's ability to continue forming stars. This feedback loop ensures that galaxies and their black holes evolve in step rather than diverging wildly. In the Milky Way, this relationship is subtler than in massive elliptical galaxies with blazing quasars at their centers, but it still holds. Sagittarius A's mass, 4 million suns, is exactly in the range predicted for a galaxy with the Milky Way's bulge mass and velocity structure. The black hole is neither undergrown nor overgrown. It is proportional to its surroundings, a sign that whatever processes governed co-evolution have acted here as well. Simulations of galaxy formation show that even modest periods of black hole activity, like those seen in the Milky Way's past, can regulate gas flow, star formation, and the growth of the bulge. The energy needed to influence the central kiloparsec isn't enormous relative to cosmic scales. A few well-timed outbursts can heat gas, suppress star formation, and alter the fate of infalling material. In this way, Sagittarius A star has shaped not only the structure of the central regions, but also the long-term evolution of the galaxy. There is another, more subtle way in which the black hole shapes the Milky Way, its role in maintaining dynamical order. The orbits of stars throughout the inner few thousand light-years respond to the combined gravitational field of the bulge, bar, and black hole. If the central black hole were absent, simulations show that the bar could become unstable, perhaps even dissolve over billions of years. Gas inflow to the central regions would change dramatically. Star formation could proceed unchecked, altering the age distribution of stars in the bulge, and the core might puff outward, losing some of its dense, compact structure. With Sagittarius A star in place, the gravitational potential well remains deep and sharply defined. This anchors the orbits of stars in the bar, helping maintain the observed peanut-shaped bulge that results from bar buckling. It keeps gas flows to the center predictable, even if intermittent, and it ensures that the central parsec remains a dynamically distinct region with high stellar densities and extreme orbital velocities. On the largest scales, the influence becomes more abstract, but no less important. The Milky Way's spiral structure, The elegant arms winding around the disk does not depend on the black hole directly, but the overall mass distribution of the galaxy does. A central mass helps stabilize the rotation curve and contributes to the balance between the disk and bulge. In this sense, Sagittarius A star is a keystone in the massive gravitational architecture that defines our galaxy's shape, balance, and long-term behavior. Even the halo, the vast diffuse envelope of dark matter and ancient stars, responds indirectly to the black hole's presence, because the structure of the inner galaxy influences how orbits and mass distributions evolve over cosmic time. Remove Sagittarius A star, and the entire Milky Way becomes a fundamentally different system. It is easy to think of Sagittarius A star simply as a quiet black hole surrounded by a few flaring events and orbiting stars, but its influence extends far beyond the lightless boundary of its horizon. It shapes the central bulge, stabilizes the bar, regulates star formation, and ensures the galaxy evolves along a path consistent with the universal link between galaxies and their black holes. In a very real sense, the Milky Way is the galaxy it is because Sagittarius A star is the black hole it is, neither too active nor too dormant, neither underpowered nor overwhelmingly luminous. Its gravity sculpts the orbits of stars. Its past outbursts sculpted the flow of gas. Its mass anchors the structure of the bulge. Its quiet now allows the central region to exist in a delicate balance. It is not merely an object at the center of the galaxy. It is, in many ways, the center of the galaxy's identity. The closer one studies Sagittarius A star, the more its presence begins to feel less like an astrophysical object and more like a kind of cosmic metaphor, a reminder that the universe is shaped as much by silence as by spectacle. For all its mass, all its gravity, all the violence it is capable of unleashing, the black hole at the center of the Milky Way now sits in quiet equilibrium. It neither demands attention nor radiates power. It simply waits, and yet the galaxy orbits around that waiting. It's a strange thought. Everything we see in the night sky, every star, every nebula, every drifting planet, every long arc of spiral arms, turns slowly around something that emits almost nothing at all. The heart of the Milky Way is not a brilliant beacon, but a dark well, a space carved out by a hunger so complete that not even light escapes. From that silence comes order. From that stillness comes motion. It is a gravitational anchor for 100 billion stars, an invisible point around which the entire disk gently rotates. There's something quietly unsettling about this, and something deeply beautiful. When astronomers look beyond the Milky Way, they see the same pattern repeated everywhere. Virtually every large galaxy, no matter how luminous or obscure, hides a supermassive black hole in its core. Some blaze with furious accretion, lighting the edges of the observable universe as quasars. Others simmer in dusty shrouds, waiting for the next stray cloud to wander too close. Some launch jets that travel millions of light years. Others, like ours, lie nearly dormant, whispering in radio waves and pulsing with occasional flares. But they are always there. These central black holes are not strange exceptions. They are, unexpectedly, the rule. It means that galaxies and black holes evolve together, bound by physics and by history, shaping one another in ways both dramatic and subtle. A black hole is not added to a galaxy like a jewel at its center. It grows with the galaxy, eats with the galaxy, rests when the galaxy rests, and ignites when the galaxy delivers fuel. Over billions of years, it becomes an inseparable partner in the galaxy's life. This makes Sagittarius A something more than a distant curiosity. It is part of the structure that made us possible. The stars that formed the sun, the gas clouds that collapsed into planets, the motions that shaped the spiral arms. All of these unfolded in a gravitational architecture stabilized by a massive object in the center. We orbit the galaxy not because the black hole pulls us directly, but because its presence helps define the overall balance of forces. It is one of the elements, dark matter, stars, gas, and this hidden core that holds the Milky Way together. That a universe filled with chaos and energy would rely so heavily on something perfectly silent feels like a contradiction. But nature often works that way. The quietest processes guide the loudest ones. The unseen structure determines the visible form. The black hole, which seems like the ultimate expression of cosmic violence, is also an example of cosmic restraint. There is violence in its past, periods of bright accretion, outbursts powerful enough to carve bubbles thousands of light years wide, flares that lit up the galactic center, but there is a stillness in its present that feels almost contemplative. It consumes at a trickle. It glows faintly. It shapes without announcing itself. A silent influence, patient and immense. This duality reflects something universal about cosmic evolution. The interplay between creation and destruction, motion and quiet, energy and emptiness. Stars are born in clouds that collapse, erupt, or are shredded by radiation. Galaxies grow through collisions, mergers, and long periods of drift. Black holes ignite brilliantly when they feed, then fade into long epochs of waiting. Everything balances between extremes. Sagittarius. A star embodies this tension. It is one of the most extreme objects in the universe, yet at the same time it is among the most composed. The event horizon represents pure finality. Light that goes in does not come out. But the black hole's influence is steady, gentle even, over much of the galaxy. It governs without spectacle. It endures without expression. The violence is potential, not constant. And that potential is a reminder that stillness is not the absence of power. It is power held in reserve. For billions of years, the Milky Way has orbited this quiet hunger at its core. Stars have risen and died. Clouds have formed and dissipated. Clusters have spiraled inward and scattered. And through all of it, the black hole has remained mostly silent. It has not needed to blaze to shape the galaxy. Its gravitational well is enough. There is something humbling in knowing that the most massive single object in our galactic home does not shine. There is something grounding in realizing that we live not in a universe defined only by explosions and radiation, but also by structures that exist precisely because something is missing, because matter has fallen into a darkness we cannot see. We are used to thinking of creation as brightness, but the galaxy suggests otherwise. Sometimes creation comes from stability, sometimes from absence, sometimes from a quiet center that holds everything together. As our telescopes become more sensitive, and as projects like the Event Horizon Telescope refine the resolution of the black hole's silhouette, we'll learn more about the physics near its edge, how plasma twists, how magnetic fields snap, how light curves around the event horizon. But none of that will change the philosophical simplicity of the picture. At the heart of our galaxy is a void, a place where matter has been removed from the universe yet still influences everything within it. That idea feels heavy and serene at the same time. It challenges the instinct to associate importance with brightness. It suggests that power does not always express itself in noise or activity. Sometimes it expresses itself in being still, in being constant, in anchoring the space around it without demanding attention. Sagittarius A star is a reminder that even in a cosmos built on energy, motion, and change, there is room for quietness. Quietness that shapes galaxies, guides stars, and holds the center of everything we know. It is a reminder that stillness can move worlds, that absence can create structure, that silence can hold an entire galaxy together.